SSTs, as I will present later. I will briefly mention the LSTs. And in both cases, the project is under the supervision of Elisabete Gouveia Dal Pino, who is the PI of the thematic project that is funding part of the SSTs, and also Ulisses, who is here and is going to talk about SWGO, but he's also part of the CTAO and a member of the team of the LSTs. It's this one. No? No. I can use the laptop, don't worry. Yes.
I think it's true.
Okay. So a brief history about the observation of cosmic rays and gamma rays in space. So the first measurements about the cosmic rays happened in the early 1910s with Victor Hess experiments with balloons at high altitude. He was able to identify electric charged particles with high energies reaching the Earth on the high atmosphere. And later on, Pavel Cherenkov discovered the Cherenkov effect, which is very interesting because as these particles are very energetic, they eventually, as they enter the atmosphere with speeds higher than the speed of light, they will decay in energy and produce, especially produce this bluish color light that you can see in tank reactors and also in the atmosphere. It's very difficult to measure this because it's very dim light, and this process happens in a very short time scale. So the physics was well known since the 30s, but the technical issue in order to measure this effect in the atmosphere has been developed much later. So what we are going to talk about is in the spectrum of electromagnetic waves is at the high end here, something between 10 to 11 to 10 to 15 electron volts. CTA is going to focus on the TeV range, hundreds of GeVs and tens of TeVs. This is a window that will probe very interesting physics, both for particle physics, because we are going to probe, for instance, models of dark matter annihilation. So we will be able to determine what's the particles that compose the dark matter of the universe, but also for the astrophysics itself, because we are going to observe high energy processes in astrophysical objects. So it's important in the two ends. So historically, the first detection of Cherenkov effect in the atmosphere was in 1989 with the Whipple Observatory, the Smithsonian. And after that, several other instruments started to pursue the detection of the Cherenkov light in the atmosphere, which is the technical approach of the CTAO. The idea is that the gamma ray, or even other particles, they will interact with the atmosphere, creating the air shower, which is the production of pairs of positrons and electrons, which will also slow down, producing more gamma rays or photons with lower energies. And eventually, this will cascade into a flash of this bluish light. And this bluish light will be detected by regular telescopes. So the idea of the Cherenkov effect in the atmosphere is to just observe light as it is with regular telescopes, but not as regular as what we know because of these all technical issues that I said. It has to be very sensitive because the light's very dim, and it has to measure this pulse of light in nanoseconds. So the cameras, they cannot be on for minutes or hours as we do in regular observatories. The cameras, they have to produce images very quickly. So the major TV range observatories in the world are the Veritas, the US, MAGIC, and HES in Africa. And these are also combined to water tank laboratories as SPOC and currently LASO for its very recent commissioning of LASO. And these instruments are what we know nowadays in high energy astrophysics as the main detectors. With these instruments, the sky of high energy sources has improved a lot. So remember that by 89, we just had Crabbe Nebula as the single object measured. So for the last 30 years, the sky now, this is the map of the sky now is more or less fully covered. So we have extragalactic sources, mostly these red balls here, they represent more isotropically the universe. So it's probably more external to our galaxy. And also here in the galactic plane, you see several objects being measured. They are mostly related to supernova remnants, pulsar wind nebula, and star-forming regions. So these are the main particle accelerators in the local universe. The idea is to increase this map and observe better these objects, well-known objects, with better resolution, spatial resolution, in order to map where in these objects we are accelerating these particles, and also with higher sensitivity to determine more objects, because we plan, we plan to increase the number of known objects by a few factors of tens. So our estimates is that in the TeV range or above TeV range, we are observing more or less 10% of the detectable objects in this range of energies. So the idea to build CTA, the CTA Observatory, was to beat the sensitivity level of the current instruments by 1 order of magnitude at the TeV range, boost the detection area, because then you have access to very short timescale phenomena like GRBs, gamma ray bursts, to improve the angular resolution. So then you can, as I said, you can well resolve the sources of the gamma rays that are already known, and get the energy coverage wider, because these instruments that I mentioned, they are narrower in terms of range of energies. So they are limited to a few processes. With the CTAO, the idea of building CTAO was to get a very wide range of energies. So you can go to local universe sources and also cosmic sources. And also the idea of CTAO was to, in the concept of CTAO, is to get the entire sky. So that's why CTAO is going to be built in 2 sites, one in the northern hemisphere and one in the southern hemisphere. So CTAO will be the major facility in high energy and very high energy photon astronomy over the next decade and beyond. So I will show later on the schedule, but the idea is to have by 5 years from now, the instrument operating. So from 2030 to 2040 or beyond, it will be the major high energy facility in the world. This is the list of members, the map actually, of members of CTAO. It's a big project. It costs, the current cost book tells us about 400 million euro. This is the total cost of the project. And it has more than 31 countries. It has 31 countries, more than 200 institutes, participating on the project. So the Brazilian contribution is being given by all these institutes here. So I'm from the University of São Paulo, as well as Elisabete, and CBPF here represented by Ulisses. What kind of science will be done with CTAO? As I mentioned, we can go from cosmic particle acceleration, so to understand how the particles are being accelerated in the astrophysical sources, up to or down to, in terms of scale, the physics of dark matter, symmetry, Lorentz invariant testing, and all these interesting astroparticle or particle physics in terms of the theoretical approach. So the design of the CTA, in order to deliver this to us, is to have 3 types of telescopes. We have the large telescopes, the medium, and the small telescopes. These are being designed. They were designed. Designs are done. So the designs, they were produced in order to probe different regions and different energy ranges. So the sources that will be mostly detected by the LSTs are those with lower energies. And these are more or less related to very distant objects, because the gamma ray suffers from interaction with the background radiation. So it damps as it propagates through the universe. So you cannot measure very high energy gamma rays coming from distant galaxies. So the most energetic gamma rays detected by CTAO are coming from nearby sources, mostly galactic sources. And this will be basically probed by these small telescopes. So this is the blueprint of those. And this is how they are going to be placed on these 2 sites. So the southern site is going to be in the Atacama Desert in Chile. Currently, what we call the alpha configuration is the first configuration fully designed for science, but it will be improved later on. After its commissioning, it will be, depending on budget, it will be improved by the increase of the number of telescopes. So far in the alpha configuration, we have 37 small telescopes plus 14 medium telescopes, and 2 large telescopes are already with the budget secured. So it will happen. The construction of the site is this design here. So this light blue cyan is the location of the SSTs, and in the darker blue, the MSTs. And here in dashed areas, the planned 4 LSTs, but currently 2 have the budget secured. And in the Northern Hemisphere, we have in the Canary Islands, the 4 LSTs and 9 MSTs. So the Northern Hemisphere site is going to be focused on the distant universe. This is mostly because they are away of the galactic center. So the galaxy is not in front of the objects that they want to observe, because the galactic center is in the southern hemisphere. So this will be the target of the southern side, because you have these small telescopes. The sensitivity of the instrument is going to be at least 1 order of magnitude better than the current instruments. So here is the sensitivity of MAGIC, Veritas, Fermi, HAWK, and LASSO. These are for, at least for MAGIC and Veritas, you see for the same time, CTA is going to be at least 1 order of magnitude better. And also increase the range of detection up to hundreds of TeVs. So this is what we expect to have already in 2030. So let's talk about the telescope. So the large telescopes are being built. One is already operational in the Canary Islands. So there is science coming from this LST1. So the CBPF team is contributing to all the phases. So they helped with the design, the construction, and the installation. The budget provided by Brazil for LSTs were around 500K. And the specifications is, it's a massive telescope. It's 23-meter diameter, effective area of over 350 square meters, 45-meter high, 100 tons, and only just 20 seconds to point. So once you define the object that you want to observe, it takes only 20 seconds to reposition this telescope. So the mechanics is really, really awesome. And it's designed to have higher sensitivity at 20 to 150 GeV. So it's probing the lowest energies of the CTAO. So this is an announcement of a discovery of LST1. So it was from December last year. So it was already doing very nice science. So it's the first or the most distant AGN ever detected by a Cherenkov telescope, just one single large telescope. Imagine what we can do with 4 combined with the MSTs. So it's very interesting science that's coming in. About the SSTs, we're going to build 37 SSTs in the CTAO South in Chile. The design has been approved last year. Elisabete is going to talk about ASTRI mini array. The mechanics and the optics of ASTRI is the same as the CTAO. So both projects, they are more or less connected. The specifications is that it's a small telescope, 4 meters in diameter, effective area of 5 square meters. It's very, you wonder why only 5, because the diameter is 4 meters, but it's because this makes an obstruction of the light. This is where the second mirror is, so it reduces the effective area, but still is the amount of telescopes is high enough to have the largest collective area of all telescopes. So if you sum up all the area of these SSTs, we'll have more mirrors, more collecting areas than any other observatory in the world. So it's 9 meters high and over 7 tons in weight. It's equipped with a camera that, what's the most important point is that it is a fast image processing. So it creates 128 frame movie in less than 1 billionth of a second. So this is what we need in order to prove very quick objects like GRB. So you have to understand how the energy is changing in a burst of gamma rays. And in order to do this, you have to create very quick measurements. And in the current instruments, you don't reach this frequency of detection. And it's designed to operate at 5 to 300 TeVs with maximum sensitivity around 10 to 100 TeV. So it's probing objects which are closer. So we are talking about supernova remnants, pulsar wind nebula, and star-forming regions. So Brazilian contribution to the SST is our team, so led by Elisabete. So currently we have about 60 members being, we have about 30 members in the SST, which represents more or less 50% of the Brazilian contribution to the CTAO. Our budget is now for CTAO about $1 million. And this will be mostly applied to the assembly, integration, and verification phase. which is once the telescopes are built, they're going to be built in Italy and in France, and they will be delivered in Chile, and we will help on the mounting and verification of the instruments. So my time's done, sorry. Okay, so let me quickly talk about the status. So the schedule. So the thing is, now we may say that CTAO is going to happen, the budget is secured, all the policies are finalized, and we will have 5 SSTs in Chile by the next year. This will be enough for initial science making, and then all the rest of the SSTs are going to be delivered by 2029, and then the full science is going to happen in 2030. This is the schedule that we have. So I will leave here my conclusions, and you may ask anything about this TO. Thank you. By the time.
I have a fantastic thought. I have a question about this movie, 128 frames. Is it continuously?
No. Yeah.
What was the trigger?
Yeah. The thing is important is it generates petabytes in an hour.
Yes.
So there is no point of collecting random data and then looking after.
Right.
So the CTO is going to operate by demand. So you point to some object.
So someone else has to tell you where to point.
Yes, it can be a trigger. No, it can be a trigger. CTO can be a trigger, but also it can respond to triggers. So someone detected, for instance, in neutrino flux, and then it warns, and then you go to the gamma ray. And but also, of course, there are the key science projects. The key science projects is going to be, well, it's not defined, but it's about 30% of the time for the next 10 years. And then we know the sources. Yeah, we know the sources, and then we will
be a galactic plane survey, and then
yes. Some AGNs, which are already know. Yeah, dark matter, we know that, okay, if you look to Perseus, you supposedly you can get some flux. So you know some objects.
Great,
but it can be triggered.
Fantastic.
So just for comments that this timeline for the SSTs in the south is very interesting because you have initial seed of the high energy part of the array. And next year we should start a small engineering array of SWGO. So I guess we have the elements to start working out the synergies and and how to work with the instruments together.
Yes.
And we are going to be very close.
Yes, the same. I'm on the same side. Yes.
Paraná. Close to Paraná.
Yeah, but everybody will meet there.
It will be crowded.
I don't see question from Zoom. No, well, let's thank again.
Thank you.
Dal Pino. She will tell us about the ASTRI mini array.
A CTAO precursor.
Yeah, the CTO precursor.
Yeah, Diego has already paved the way for my talk because he talked about the CTAO and all the technicalities. So it's going to be easier to introduce the ASTRI mini array, a CTA precursor.
I don't know. It's not working today.
Because of me, perhaps, because I'm magnetized, I always. Let me see. It's working.
The pointer will not show there because it's a laser.
It's only to, okay.
Need to change size.
Oh God, there is light. Okay, so CTA precursor.
Does it help if I put in myself?
Yeah, I think, yeah, thank you, because I cannot see. Okay, that's, so,
Now you cannot.
so This is the next generation of Cherenkov telescope facilities, observatories, on the ASTRI mini array itself, that will be a precursor for the CTAO with 9 telescopes, 9 small-sized telescopes. The CTAO, both south, represented in this diagram, in this image, that is a sketch, of course, and the CTA North. Diego talked about the CTA already, and also the forthcoming LASFC, the large array Cherenkov telescope that will be built at the same site of LASU. As Diego mentioned, LASU is a facility with Cherenkov tanks, as SWGO will be in the South Hemisphere. But here are essentially the next generation of Cherenkov telescope facilities. So CTA mini array ASTRI is now in construction in La Palma, in Tenerife Island, in the Observatory Tide, and it will have 9 small-sized telescopes, and the countries that are allowing for this are all members of the CTAO. Italy, Brazil, South Africa, Spain, and Switzerland. Recently, Spain and Switzerland have joined. It will have 9 small-sized telescopes. There was a movie showing how this telescope works, but I will explain later on. So the site is here represented. There will be the 9 telescopes will be distributed along this region. The first one is already installed over there, the ASTRI 1. And as Diego mentioned, the ASTRI structure will be the same that was actually chosen to be the structure that will compose the small-sized telescopes of CTAO. Actually, the prototype was built in the framework of the CTAO collaboration, and then it was chosen out of 2 other prototypes of the small-sized telescopes to be the one that will be constructed for the 37 small-sized telescopes of the Cherenkov telescope array. Okay. So it's important to put the ASTRI mini array in the context of the Cherenkov telescope facilities in the world. The ASTRI mini array will be the largest Cherenkov facility until the construction of CTAO and the starting of the CTAO operation. So it's going to be the technological runner for CTAO small-sized telescopes, in the sense that the small-sized telescopes will be completely tested in the ASTRI mini array. The SST consortium will have 37 complete Cherenkov telescopes, as Diego mentioned, and these are to be delivered over the next 5 years. 5 of them at the end of the next year. The optical and the electromechanical structures are similar. Actually, they are identical in the sense that the SSTs will be with the ASTRI design, the same ASTRI design structure. Just the camera that is going to be an appropriate one that was fully developed in the framework by other collaborators in the CTAO collaboration, the Czech camera. And the ASTRI mini array, therefore, will be essential. It will be a central training ground to optimize methods and approaches for the production, quality assurance processes, and the assembly, integration, testing, and verification activities of the SST telescopes for the next years. Besides, of course, doing science well before the operation of the CTAO. So let me give you some historical approach on the construction of the ASTRI prototype. As I said, the ASTRI, the SST telescope prototype was developed in the framework of the CTAO collaboration. It was inaugurated, the first version of it, that one, that heavier one was inaugurated in September 2014. And after that, it suffered several changes and it became this much lighter and flexible structure. And this was the final design, and this is the current SST, ASTRI SST, that is already installed in the Tenerife Tide site. The technical properties of this telescope, as Diego mentioned. Okay, it's a telescope with two mirrors. The primary mirror has 4.3 meters diameter, and it's a mosaic mirror with 18 segments. And the second mirror is a monolithic one with 1.8 meter. And this is very original in the sense that this is a Schwarzschild-Coudet configuration that was well known and very that enhanced a lot in optical telescopes, the entire optical system. And this was implemented for the first time in a gamma ray Cherenkov telescope by the ASTRI collaboration. And so the focus parameter is 0.5. And as Diego mentioned, the average effective area per telescope is 5 square meters. And the Cherenkov camera is full of silicon photon multipliers. Actually, there are with a total number of pixels of more than 2,000, which makes and with a size per pixel of 0.19 degrees. And this makes the field of view of these cameras, it's amazing. It's 10.5 degrees, which allows for, for multiple observations of several sources, point sources, and also allows for doing observations of extended sources. So resolve extended sources in gamma rays. This is challenging, very challenging. So it's going to be amazing. And the energy range of sensitivities between a few TeVs to a few hundred TeVs. So it's the extreme of the window of the gamma ray window to probe the most energetic sources in the universe. As Diego mentioned, these are, of course, the probability of observing these sources in the nearby universe, in our galaxy, and the nearby universe is bigger, but it's also possible for distant sources, as we are going to see in a minute. So the integration factories are both in Italy. There are two factories in Italy finishing the construction of these structures. So we see all the pieces being assembling, and also here we can see monolithic sample of the mirror. And so as I mentioned, there are two factories. One of them is finishing the ASTRI telescopes number 8 and 9, and these will be delivered, commissioned, and on the site in December. And here, the other factory near near Milano, is building and finishing the other 6 telescopes. I should mention that here in Brazil, we, with FAPESP funding, we could not only help with the development of the ASTRI prototype telescope, but also to support 3 of the telescopes of the 9 telescopes of the mini array in a former thematic project with funding, of course, by FAPESP. And okay, this is the computer center on site. There is another one in Rome, and the observations will be completely, can be done completely remotely. And of course, storage is a problem, as everywhere nowadays, storing data in astronomy or in physics or in science, and astroparticle physics and particle physics is a major challenge, but this is also under control. I should say that we had, during all these years, 2 Brazilian engineers participating in the structure, camera, and software development. These 2 engineers actually are over there on that picture up there. I'm there as well. This was in Catania in the inauguration of the ASTRI prototype, the first one, the horn, the big one, the heavy one, that one. But they are here. And actually here is Carlos Firmino. He was participating in the assembling and testing of the ASTRI-1 installation in Deltide in Tenerife in 2022 and 3. And okay, here, one of them participated, actually, he was in charge of the front end of the camera. So in the first phases of the camera, he developed this part. And so he is a mechatronic engineer, so he could develop the software of pointing the telescope. So these guys, they really collaborated. And I think if we can say that in Brazil, we have 2 people able to build a telescope from, from end-to-end telescope, from the base to the top, these are the guys, these 2 engineers. They really know a Cherenkov telescope from point to point, are the only ones in Brazil, I can say. Here, the mini array performance. So Diego showed this with regard to CTAO, but I should say that the ASTRI mini array, okay, the ASTRI mini array is here, right? The sensitivity. The sensitivity of the ASTRI mini array will be superior to the CTA North, for instance, right? And comparative with the CTA North where is the CTA? Yes, it's in here, actually.
The dotted line.
Yes, the dotted line. And these are the current ones Magic, Veritas has. So they are really, it's going to be just at the CTA North has this range of achievement, and the ASTRI mini array will go all the way up. So essentially, and of course, it's the sensitivity here at smaller scales is smaller than that of the CTA North, but they will be very complementary until the construction of the full CTA. It will be the largest one compared with the current ones, right? So this is when CTA North will be ready, right? And of course, CTA South will have a sensitivity better, but until the construction, the ASTRI mini array will be the biggest gamma ray observatory facility. And here we compare the ASTRI mini array sensitivity with the current tank-based facilities. LASO in the south, in China, not in the south in China, and HECAP in Mexico, New Mexico. So we see that the sensitivity of LASO at the largest, the 100 TeVs, is bigger. But because it's a tank-based, the resolution, the angular resolution is very poor, right? And therefore, these two facilities will be also very complementary as well, as I explained better in here. So we have here these diagrams. Let me speed up. But these diagrams show the angular resolution, the energy resolution, and here the sensitivity, the normalized compared with the MAGIC, for instance. So it's enormous, the sensitivity compared with the current Cherenkov telescope observatories. And it's going to be bigger, not only the sensitivity better by a factor of, by several orders of magnitude, actually, at the highest energies than the current IACTs, but the angular resolution as well, and the energy resolution by 10%, and the energy, the angular resolution 0.05 degrees, which is amazing in gamma rays, right? And for you guys to have an idea, the angular resolution of the LASO and HECAP, it's 1 degree. So you really do not solve the source, right? So with ASTRI, and of course, a very large field of view will be excellent to probe these two features, to probe extended sources morphologies and also multi-target fields with this large field of view, and also serendipitous discoveries, right? And see something over there. So the ASTRI mini array is mini, but not small. It's going to be the largest AICT until CTAO will be ready, and with all these capabilities, right? Let me say a few words very quickly about the science. It's essentially the same science case of CTAO. So it will probe the origin of cosmic ray accelerators, and also probe with the pevatron sources that produce cosmic rays, ultra high energy cosmic rays that are pevatron emitters. It will probe particle propagation. It will probe the cutoff of the spectrum of these sources, because at TVs, we are talking about TV gamma rays, and transients as well, like gamma ray bursts, and fundamental physics. It will put constraints on the extragalactic background light produced by the first stars and first galaxies, because this radiation actually absorb part of the gamma rays that are traveling from very distant sources. So it puts constraints on EBL and therefore on cosmological models. It probes the intergalactic cosmic magnetic fields, because these gamma rays also being absorbed, interacting with these background photon fields, CMB, and extragalactic background light, they also produce pairs, electron-positron pairs, that interact with the underlying intergalactic magnetic fields, and therefore we can put constraints, we can measure indirectly these cosmic magnetic fields, very small intense magnetic fields in the cosmos, and also can put some constraints on the chemical composition of relativistic jets from very distant blazars and AGN jets, because we don't know yet if they have hadrons or only leptons. So we can put constraints, because we can solve the cascading of these sources in pions, in neutrinos, and then we can say, okay, we have hadrons there, right? And also tests on action-like particles, dark matter candidates that can also oscillate between gamma rays, traveling gamma rays in background magnetic fields, can either, produce axions. So we can probe, put constraints on this population as well. So all these physics, it's going to be amazing. And, you know, with the synergies with all areas of physics and cosmology, particle physics and cosmology, beyond, it's over, okay. This is also interesting physics, but I do not have time to talk about this because LASO has discovered new gamma ray sources at hundreds of TeVs and 1.4 PeV that, but the resolution is so bad that we don't know what are these sources. And with ASTRI mini array, we'll be able to identify and probe the morphology and spectra of these sources. So this is going to be happening next year, in 2 years, a couple of years. It will probe also gamma ray bursts as because this source, that source, GRB, it's a very distant source, and it was observed energy emitting at 10 TeVs. This was before considered impossible for these distant gamma ray bursts because this energy should be absorbed in the wave. So there is something wrong with our physics or the cosmological models with the transparency of the extragalactic background light produced by first stars and first galaxies. So we don't know what's going on here yet. And of course, these upper limits, this energy cutoff will be measured by ASTRI mini array. Current master schedule, ASTRI 1 telescope is going to be completely fully accepted and ready to observe by October. Sorry, it was accepted in October. It will be fully observing at September now. And 2 more telescopes will be installed until the end of September, 2 more until the end of October. So the rest of the mini array is expected to be completed next year, installed fully, and the end of the year, we may start operations. Just to mention about this budget that Diego has mentioned. So we got in a former thematic project financing about $4 million for the first part for the ASTRI mini array. And currently we have to develop the AIV activities in the construction of the SSTs, $1 million more. I leave you with this summary and sorry for.
You didn't lose your touch.
No. Same. Same. Oh, yeah.
From Zoom, questions for Zoom? No?
So I think
So,
everybody's
that's
happy
like-
with the CTAO and ASTRI mini array enough of it.
Thank you. So our next speaker is, Ulisses. So, we have Ulisses de Almeida. He will tell us about SWGO.
So this is working too fast. Yes. Good. Okay. So now we move to the other technique of ground-based gamma ray astronomy, which is SWGO, Planet Observatory in the South. And I talk on behalf of the SWGO collaboration. Since I knew my predecessors would speak a lot about the science, I go directly to the instrument and the perspective. So I'm not going to discuss very much the science that can be done because it was covered. So a quick introduction about some aspects of the field that have not been exhausted yet. Then I will talk about the SWGO research and development phase, which we are just finishing. In fact, the main news we have is the site selection, and even more than we expected, site selection is really a collapse of the wave function. Everything follows from that very quickly. So, and then I'm going to tell you the news about that. So the ground-based gamma ray astronomy network is very large. You can see the gray points there are the current instruments. So you have 3 current IACT observatories operating: Veritas in the US, MAGIC in the Canary Islands, and HES, which is the only ground-based gamma ray observatory in the south since 2005, installed in Namibia. Recently, and then of course there is HAWK, which is a particle array detector that complements the IACTs in Mexico as a dual country, essentially collaboration with US and Mexico. Now there are more institutes involved. There are some institutes in Germany and a few other, but it was originally Mexico and US endeavor. LASO has recently joined. It started construction in the middle of past decade. And in 2019, 2020, it started putting out the first results. It was completed in 2021 and has been since then revolutionary, as Betty already pointed out with the discovery, for example, of the pevatron sources in the galaxy and the observation of the brightest GRB of all time with an amazing statistics that allowed us to already do a lot of GRB science with a single event detected by this instrument. It is the leading instrument in the field. It is the benchmark, and SWGO is intending to do what LASO is doing in the north, in the southern hemisphere. It's important to observe that SWGO will be the first ground-based particle detector array for gamma ray astronomy in the south. So essentially, as it's complementary in some aspects to the IACTs and to what CTA will do, it is a new astronomical window that will be opened. One of the very few remaining astronomical windows. So just to highlight some differences, people already talked about the complementarity of the two techniques. So basically the IACTs, they are atmospheric Cherenkov telescopes. So they are pointing instruments that see the Cherenkov light produced by the secondary particles of the showers in the atmosphere. So this gives them some advantages, which is that they have a large sensitivity, and they also have a very good shower reconstruction capability, therefore good angular and energy resolution. And this is easy to understand. As the Cherenkov light propagates all the way down to the ground, where the telescope is installed, you are following the complete development of the shower. So you are exploring the calorimetry of the atmosphere fully to do that. So this is very good. It gives them a lot of sensitivity. But the downside is that they can only observe at night, and in nights where there is no moon, because the Cherenkov light is very dim. So this means that they have a duty cycle of about 15% over the whole time of the year. This amounts to 1,500 hours more or less of observations. And this means that there is limited science that can be done with that amount of time. Typical integration times for weak sources are 50 hours, so you can see where we are going there. The particle arrays, they have a bigger restriction in terms of how well they can reconstruct the shower, because they are not following the whole development of the shower, but they are taking a snapshot of the state of the shower at a certain height. So when the shower crosses the particle detectors, it takes essentially a picture of the state of the shower with all the fluctuations and everything that you are. And this is basically due to the fact that the first interaction point in the atmosphere can vary a lot, and you are restricted, therefore, to that information. The advantage they have is that you are observing the Cherenkov lights inside the tank. So if you're using scintillators, you are not caring about how also the status of, I mean, it's a particle detector instrument, so day or night doesn't make any difference. And this means in the end that you have a continuous duty cycle. So even if initially your sensitivity is not so large at a certain energy, you are continuously integrating the source the sky as it transits over you. So over the years, you accumulate quite a lot of sensitivity, actually. And you have a wide field of view, which allows things like what LASO did, detecting a very strong GRB on the field of view when it explodes. So you don't have the problems of the delay. So it's a very interesting instrument, and you can see how complementary it can be to IACTs. Another thing to mention is the ultra high energy performance. I mean, the fluxes of the gamma ray sources at these high energies, above several tens of TeV up to the PV, they fall with a slope of minus 3.5. So it's a steep fall. But since these guys are integrating continuously the sources, and they have a huge effective area of kilometers square in the case of LASO, you can still perform at the extreme energies. In fact, there is one PV photon from a crab-like source every year that is detected by LASO. But as you integrate, you can detect these sources. And LASO has an advantage, which every telescope that aims to operate in these energies should seek, which is basically background free. Its hadronic suppression is excellent, and therefore it basically operates without background. So there you can see the comparison of the field of view of the two instruments. LASO with instantaneous field of view of 1/7 of the sky, and the others limited to something like 5 to 10 degrees. So they're very complementary in many senses. And in the case of the ground particle detectors, this has been more or less the story. So first of all, the observatories have grown larger over time, consistently larger over time. So you start here with in the early 2000s with the precursors or the first generation of these instruments. Then you have HECAP that you heard about already today with 60,000 square meters in area, a dense score of 20,000 square meters in area, and Tibet, which is in some ways very similar to the outer array of LASO, similar size, and of course LASO with 1 kilometer square of area, basically divided into a core, which is a pool for Cherenkov, water Cherenkov detection, and then an array of scintillators and underground Cherenkov tanks to observe the muons to do hadronic suppression at excellent sensitivity. And the other thing that has happened with these observatories is that they have gone higher in altitude. And this is simply because although the Cherenkov light reaches the ground, wherever you are, the particles don't. So they develop 10 kilometers high in the atmosphere, but then at a few kilometers, 4 or 5 kilometers, even the strongest showers have already been completely dissipated in terms of the particle content. So for doing PV astronomy, ultra-high energy gamma ray astronomy, you really want to be as close as you can to the shower maximum. And this is more or less 5 kilometers in altitude. And that's why we are going in that direction. So you have the better information content of the shower. So SWGO is going to be a software instrument. That's the obvious move for the field, and the reason is very clear. So you can see here, first it's going to be the first to be there of this technology. So this would be already interesting. But this part marked with the green is the field of view of the galaxy of LAS1 HECAP. So you see that they are missing two very crucial things. They are missing the galactic center from their observation field of view, and they are missing the synergies with CTA South, which is this blue market area here. So SWGO really wants to achieve both explore the synergy with CTAO and observe the center of the galaxy, which is the best source for dark matter signal detection with this technology or with gamma rays, ground-based gamma rays. And is the region of the galaxy where you have the highest concentration of high energy astrophysical sources. So to understand the cosmic ray content of the galaxy, that's extremely important.
So both are missing the Crab Nebula?
No, LASO has Crab Nebula.
No, this is the and LASO has Crab Nebula, and we are going to have as well. But the fact is, this is just the galactic survey. So the field of view does get Crab Nebula, but you have that's the field of view of the galactic survey. So the SWGO collaboration is quite large. It started with 10 countries back in 2019. In fact, it was gestated in two different regions of the world. It was the fusion of an American-German initiative with a Brazilian, Portuguese, and Italian initiative, which was called LATES at the time, and was developed in 2015, 16, 17 at CBPF, when we were receiving visits from Felix Saharonian, Giorgio Mattia, and Mario Pimenta in the context of the Ciências Sem Fronteiras, so that Shellard was organizing this. So the community decided that it was best to work together, and that's how the collaboration was born with something like 9 to 10 countries, and now it has grown to 15. The last acquisitions were the Chinese from LASO that joined the collaboration, interested in exploring the physics of the South, and of course, more recently, France, that's extremely involved in CTA as well, and now is starting to get involved in SWGO. So this is the full list of countries, and we have more or less 90 institutions involved, 200 scientists collaborate. And you can see that the contingent of Latin American participants is very significant. So we have 5 countries. That's a lot, and the idea is to keep all of them involved in the project. So the international character of the collaboration is reflected in the spokes team. So there is Jim Hinton from Germany is the spokesperson. Then there are 2 spokespersons. One is myself, and the other one is Petra Huntemeyer from the US, which was at the time of the foundation of the collaboration PI of HECAP, spokesperson of HECAP. So it really reflects where the community is coming from very well. And this is the steering committee from Latin America, showing all the members. I think some of them are listed here. Our friend Claudio certainly is listening, has been listening. And in Brazil, after that selection, Elisabete will take the representation in the steering committee as well. So there is nearly 100 scientists from the continent involved and 40 institutes. That's very significant. Where are we now? So things started moving very quickly in the past years. The pandemic damped us a little bit because you cannot do much in preparation for an observatory if you don't have any idea of the sites where you're going to put it. Although we started in 2019, pandemic struck in 2020, we could only visit the sites at the end of 2022. So that held us back a little bit, but we caught up. And now we have just crossed the major milestones, the identification of the sites, and we are just finalizing the design in time for funding requests with the NSF still this year. As you see, we are in the major roadmaps of both Europe and the US, and there was even a recommendation from the Decadal Review that the US should contribute to about 1/3 of the experiment, 20 million.
LASF, you forgot LASF.
And there is LASF4RI now, yes, yes, there is LASF4RI now. I should, yes, sorry. And yes, but, and so we expect the completion of the R&D phase early next year. And then start the preparatory phase, which is basically an interim period before funding really gets in, so that we have an engineering array over next year and 2026, and by 2027 have the real construction starting with a completion in 3 or 4 years, depending on funding availability. But at least the initial phase should be available with a sensitivity superior to HECAP already in this time scale. I'm not going to talk very much about science, just saying that it's very broad, as was shown. It covers from extragalactic to the PEV sources. All our science tools are compatible with the standard software used in CTA. So the idea is that they're getting ready so that people can do predictions as well. And the white paper is in planning for the renewed expectations. Basically, the reference detector concept is based on a dense core of 80,000 square meters, so like LASO, and then a sparse array of Cherenkov tanks. This is all Cherenkov tank-based, water Cherenkov-based, that will cover 1 kilometer square. So basically, we went to cover and have a performance which is benchmarked by LASO, which is very successful. The difference is that we want to use only surface detectors, and this is for cost effectiveness. And one of the solutions that's been put forward is our standard solution, our reference solution for the array is to use double layer tanks, where you have a calorimetric layer to get the energy to do the calorimetry of the shower, and then a muon layer on the bottom. So the electromagnetic particles are stopped in the first layer, and then you just see the muons punching through for background separation. And this is what has been simulated and is proven effective. So this is a little bit the technology we're exploring, a lot of different solutions for photosensors, using, for example, multi-PMTs like the neutrino observatories do, new electronics, and of course, we're testing the tanks. These are tanks that were developed in Australia by the American collaboration, and here they are being assembled in Peru and at the HECAP site. So very similar to what they have done in HECAP. And this is a tank that we developed following the OG experience in Brazil, and here is when we met for site selection, one of these tanks at CBPF. These tanks have an interesting history. I'm going to talk about them a little bit later. So basically, to understand what would be the observatory, we went through a long 3-year process of a full simulation of a number of array configurations, using both different types of tank structure. So double layer tank, a small channel tank with multi-PMTs, that then would use the asymmetry of the first light that incites in the PMTs to detect the muons, So this involves machine learning and advanced analysis techniques, and a tank like Hawk, which separates the mules by the fact that it's very large. So although it has only one layer, the electromagnetic particles stop on the top, and the mules continue producing Cherenkov photons up to the bottom, and so you separate due to the difference in the Cherenkov yield due to the presence. And a number of different array configurations to test fill factor, footprint, and things like this. This is the Brazilian tank. This is very interesting. This R&D development, it cost 4 million reais. 1 million was paid by FAPERJ and the federal government, and 3 million was invested by the company. And the reason is, when we thought of this tank, we had a big problem. We were putting the detectors with a small 15 cubic meters of water at 5,000 meters in altitude. And freezing could be a problem to the performance. Therefore, we started discussing solutions for preventing the freezing. And together with the company, we came up with a new rotomolding technology, which is patented by the company. This is the same company that participated in the IAG construction 20 years ago, which is unique in the world. So many people said, it's impossible, we're not going to be able to do that. So now these guys are able to produce, as the only company in the world, two rotomolded tanks, one inside the other, which you inject with foam, and you keep the temperature constant to a fraction of a degree, even if you have a temperature incursion of 40 degrees outside. And this turned out to be a great product for the agribusiness, because when they have to inoculate the crops during the plantation time, variation of temperature, if the inoculation is made with biological material, it's a problem. They die, or their effectiveness is affected because it's bacteria, things like this. So this keeps them alive, so they can take these tanks to the field and store them there without any problem. And so before we had the technology being used in our R&D CBPF, they already had done the spin-off and presented it in the agri show of Ribeirão Preto 2 years ago. It's already been commercialized. Their first big bot was, how do you call it? Margin, who's using that for their crops. So there was a technological success. I think I have very little time, so I'm going to jump through the details of the R&D. I mean, we tested performance in various ways. This is showing something that we test. So what's the trade-off between a very high fill factor and a smaller fill factor of the tanks, but covering a large area? We understood that perhaps we don't have to go so high, so we can deal with a more sparse array even in the core, which is good for deployment. Also, how far can we go and how thin can you go in terms of fill factor in the outer array so that you can still detect enough muons to do gamma hadron separation? And we reproved what we already knew, that 1%, 1.5% is something that you cannot probably, so you cannot have a coverage of less than 1% or 1.5, otherwise you get very few muons. You cannot do gamma hadron separation. And this is why Jim Cronin with Casamia didn't detect the pevatrons 30 years ago. Only LASO did it now because he had, I think, 1% fill factor. He was just 0.5%, I think, off to detect pevatrons 30 years ago in the 90s. So, things are flowing. Other details about the efficiency.
You already had a Nobel Prize.
About the efficiency of gamma hadron separation, depending on the size of the tank and the size of the layers. So, but this is being very effective. So we are confident that we can do. And this is a plot that I want to ask my chair to give me some time. So here you can see one of the configurations of SWGO, composed of this double layer tank with 60 cubic meters of water and a stratified configuration just above the Cronin limit, let's call it like this, and a little bit denser ring, and the core is very dense. So you can see here that so you have the curve of CTA South, which you have already seen. You have the curve of LASO for 1 year integration, and you have the curve of SWGO in orange. And you can see that this array has the potential of matching the extremes of the energy range, the sensitivity of LASO, but it has one big advantage. LASO operates as two separate instruments, the core and the outer array. And we are going to operate as a single instrument. This is because they use different technology and it's difficult to combine because The timing of the detectors is different, so there are issues. But as operating as a single detector in this crucial range of a few tens of TV, where let's say the bulk of the day-to-day science, the survey is done, we have a factor of 10 advantage over LASFO. So this is a big thing. This is going to make a big difference.
For GRBs?
GRBs are more in
Yeah,
this region, and GRBs will always be
Yeah,
challenging.
that's true, but
But
for the-
here,
for
for the core of the galactic
brain
science,
one- No, galactic side, of course, but.
yeah, if we have another one with 10
for the-
TV, yes.
Yeah.
But I don't know when we're going to see another one with
I
this.
know. I think they're gonna have-
And this is the angular resolution, which is something that highlighted already. This is the angular resolution of LASSO for the outer array. The inner array is better, but this is for the outer array, which is where you have the galactic science. And you can see that, as was said, it around, I don't know, 30, 50 TV, it's in fact close to 1 degree. And then it goes down to something like 0.3 at the extreme energies. But these are for the different configuration of SWGO. We are going to push this a factor of several down, and particularly the core of SWGO is going to have an angular resolution which is very close to the current ACTs. So we'll be able to extend the spectrum, extend the morphology up to the high energies very well, to do physics with these particle accelerators, which is one of the difficulties that exists now, because you need to resolve the sources to do astrophysics. And SWGO will be able to do that. 1 minute and I finish. So we went through a very large process of site selection. We had candidate sites in Argentina, Chile, and Peru. They were in elevations between 4.4 and 4.8 meters above sea level, of almost 4.9. And this is because we really wanted to go up to approach the lower energies. Our requirement was a minimum available area of 1 kilometer square. Of course, we have to have a solution for water, because we are going to use something like 250,000 cubic meters of water in this observatory. And as I said, we visited there as soon as the pandemic allowed us. The sites were excellent. These are the shortlisted sites, extremely flat, so that we don't have to prepare the ground too much. The science criteria, the criteria for shortlisting included science performance, site preparation, construction costs, construction and operation risks and costs, environmental impact, and also social impact in the communities where the observatories were to be constructed. So all this was taken into consideration, and engagement with local communities was really considered a priority. The result is now out since a few weeks. We chose the Pampalabola site in the astronomical park, and we kept Timata as a backup site, which was also a very good site. So if for some reason things don't move ahead, we have a secondary site to go with SWGO. So how is Pampalabola? It's a vast plateau at 4,770 meters above sea level. These are the coordinates. It has an available area much superior to 1 kilometer square, so you can expand the observatory. And it's very close to Alma, just a few kilometers from Alma on a straight line, inside the Atacama Astronomical Park. It is 40 minutes from São Pedro de Atacama, which is an excellent base, and not more than 2 hours from the closest airport. So it's an excellent site in all perspectives. Here you can see a little bit the largest of the sites, and here, as you can see, São Pedro and the region of the park around where Alma is installed. So I'll leave you with the summary. We are closing our R&D phase in the next months and preparing for construction and funding requests. We are an international project with a large impact in Latin America, and we want to continue like that. And the collaboration is committed to do everything to improve the participation and support the participation of all the Latin American members, regardless of the site selection. And it will be the largest and the first, in fact, observatory of this kind in the South, with synergies with other instruments. So it really creates the case, or reinforces the case, for a network of astroparticle physics in this continent that really brings us and developers together and integrates the region scientifically. So thank you very much, and Paulo, please follow.
So in short, slide 18, the competitive advantage of certain energies. Does that come from the altitude? What's the main contributor there? What altitude is LASO at?
LASO is 4.4. So we are 300 meters above LASO, which makes a difference. We have an estimate. More or less, you gain sensitivity at your threshold, which is around 100, 200 GeV for these calculations, for about 10% increase per 100 meter, 90% actually. So the fact that you go higher does improve your sensitivity at low energies. But there is a number of factors. There is the technology you use. There is the density of detectors, the number of detectors, the footprint. It's a number of factors that influence. But for the low energies, it's certainly the altitude is important because the small showers, the low energy showers, they disappear. We are getting really the end of the showers at 5 kilometers. But then there is all sorts of questions related to trigger and things like this, because as you go up, the amount of noise that you get superposing showers that hit your detector, you have to separate them based on where they're coming from. So the time profile, all this comes in. It's a very challenging regime, very challenging. But if we hit that with a sensitivity that would have to be better of LASO to achieve that at these energy ranges, we would be an effective monitor of the transient sky. So bridging with what the satellites like Fermilat do, and regularly triggering CTA and detecting GRBs. But that's a difficult region.
I know that the Cherenkov tanks, these are particularly cheap, right?
Yeah.
So the cost of the tanks itself is not going to be very big. Nevertheless, you know, building this facility at 5,000 meters, 5,000 altitude is, I've been there in Alma, and you cannot breathe. You need to use oxygen all the time.
I didn't need oxygen, but it's okay. No, but no, it's if you have to be used to.
No, everybody does. Everybody needs at those altitudes. It's you know, compulsory. You are not allowed to go outside without that.
Yes,
that stuff. Yeah, because you have to move, but the workers, you know, will be there all the time putting all this stuff together. So this can make as it was in Alma, the work very expensive. What is
So we considered all these things in the cost book. So we made a detailed 1-year search and estimation of costs with the help of all the country proposers. It was really a 1-year process of making the cost book for the 3 sites. And with variations of the order of 10 to 20%, 20% on the overall observatory cost, we are around 60 to 65 million. 65 million is the price, plus or minus 20%, including everything to deliver the observatory constructed with water and instrumentation. So it's a cost-effective solution. Of course, we have to keep working hard to keep the costs in that range. But all things were considered: increased salaries because we're working in altitude, reduced working hours because we're working out. So it was a very detailed process.
Thank you. Luis Nunez.
Luis Nunez, no, so mine.
This is super tusk.
They're ready. Luis, can you try to share a screen?
Let's see.
Sure. Okay.
No.
Can you see it?
Yeah, Luis Nunez, he will tell us about LAGO. So,
Yes.
Go ahead.
Shall I go? Can you hear me? Can you see the screen?
Yes. Yes.
Now I see that you see the screen. Thanks a lot. Okay. Thanks a lot for the opportunity to share with you what we are doing in LAGO. This is an update from the last LASF4RI that we have a presentation. Okay. LAGO is, like I said, this is the world's most decentralized extended astroparticle observatory. It spans from Mexico to the Antarctica, covering different altitude and magnetic rigidity. I show you there we have and the focus, the science case is space weather and high energy astrophysics. We have water Cherenkov detector is based on water Cherenkov detector, and we have this distribution. We have one in Madrid, one in Guatemala, one in Bucaramanga, Colombia, two in Ecuador, one in Lima, and now we have two in Argentina, and we also have other sites. In fact, our network is made by 10 Latin American countries and Spain, and we are a spin-off initiative from the OYE Observatory. Now we have 83 members from 25 institutions, and as I said, from Mexico, Colombia, Paraguay. It's a wide network. Again, this is the scientific goals, astroparticle from the low energy cosmic rays. We focus on study the transient phenomena from long and short-term space weather, measuring the background of the radiation at the ground level. And very recently, we are moving to the application of the cosmic rays to other fields. I would like to stress that from the beginning, we have the idea that we have some academic goals to train Latin American students in higher energy physics and astroparticle techniques, and also to build from the bottom the Latin American network for astroparticle research. These three words are very illustrative of what we are in LAGO. We have instrumentation, we have simulation frameworks, and we have a training program. And this will guide the rest of the presentation. We use as an instrument, like other colleagues have said, water Cherenkov detector from at most from on-shelf part, in order to have a cost-effective instrumentation to look for the centralized funding scheme. Our business model is that every institution, each institution can get funding from local sources, and we have a network that share knowledge, share the designing of an instrument, and share data. This is our standard. It's not yet a standard, because every time that a group comes into the collaboration, it has their creativity and initiative, and they want to build something very special, and we have to control the management of this decentralized network is very costly. And right now we are working in a space weather station, which is not only the water Cherenkov detector, but other detectors around the water Cherenkov detector, particularly a muon detector, a VLF receiver for ionospheric space weather studies, and a lightning detector. It will be, and now we're working on that, our standard space weather station. These are two of our more extreme instrument sites, one in Marambio in the Antarctica. They have installed one of these water Cherenkov detector, and it's operating right now. We have the first result. Last year we have the first result. A lot of information from the southern part. And 2 weeks ago, the colleagues from Ecuador installed a detector at the Chimborazo volcano, or the Chimborazo mountain, around 4,500 meters. And then this is high, very high installation. Where is starting the operation right now, and we'll see what we can do with this installation. These are two other side project, like from instrumentation. One is a photon trap with Sierra Puca from the colleagues from Brazil, and these are the capability. They show the group from Bariloche show the capability of water Cherenkov detector with salt to detect neutrons. That means that we can move our detector to another field. And we in Colombia have been developing muon telescope. This is our first installation of muon telescope, and this is the newest. This is the part of are not part of LAGO, but are consequence of the LAGO activity. What has been very successful is the simulation framework. We developed a very detailed simulation framework that use Corsica, Magnetocosmic, and Jan4, and we put like a pipeline, and this pipeline can simulate the cosmic ray flux with a very detailed and a lot of physics. And it has been used to develop another application like this one to estimate the absorbed dose of the passengers and commercial and crew in commercial flights. We use article and modify to move through different altitude and different geomagnetic position. We haven't LAGO that like that, and now it's proven with the European Air Flight Association. The other is we simulate very detailed how our detector can be used to detect gamma ray burst, and it's not so good as we wanted, but they can be used. This is the simulation for all the muon program that we have been using, and we have also used the simulation framework to incorporate another trigger when we want to filter the noise in our tank. It is another paper that we have, and right now we're working how to simulate cosmic neutron to estimate the soil moisture. That means that we have to modify Corsica or use another thing. We're using Jan4 because Corsica was made for high energy particles, and those the electrons, the neutrons that are used to detect moisture are low, very low energy particles. And then we have to modify all the simulation framework. But anyhow, this is a consequence of an effort of LAGO that is being used by other people in different fields. Right now, we are also starting with the funding of CTEP, which is a network from Ibero-American countries, to a very standard use of our data. Because if we use this edge computing program, is you record the data on field, then transfer to the first site in the processing of the data, and this site are very similar to the sites that use the IoT or other devices. And then after this processing at this level, you put it in the cloud and use and share this data with all the collaboration. This is very natural for LAGO, and then now we are working to use this paradigm in our computing process. Then we have covered the instrumentation. We have also covered the simulation framework, and right now the third line of activity of LAGO is training. And then we have the pleasure to join effort with La Conga Physics. That was an Erasmus program. And it was during the pandemic epoch, because at that epoch, we have to, from La Conga, we have to use instrumentation. But we cannot go to our university and we cannot buy the instrument from La Conga. Then we asked LAGO to lend us the instrumentation that we have in different universities and how to operate those instrumentation remotely, and we did it. Then we start to collaborate from that place. And right now, starting next week, we have this international course in astroparticle and cosmology, which is shared by LAGO, La Conga, and also by CTAO. The La Conga Physics is an Erasmus project in the field of capacity building and higher education. It was a 3 but 4 year because of the pandemic, and it was a collaboration from 11 universities in Latin America and Europe, with the collaboration also of the very high, very important institute in physics. In the region, in the Northern Andes, we have 2 universities in Venezuela, 2 in Colombia, 2 in Ecuador, and 2 in Peru. Several of these universities are member of the LAGO collaboration. And right now we will start in the 2025 a new Erasmus project, which is a continuation with the scale from La Conga. And the idea is to create communities, and all the activity of this community, like courses, workshop, data, code, publication, whatever, will be shared through a Science Gateway window. Then again, LAGO, now El Bongo, is impacting the training of the astrophysics community in Latin America. The idea is this. Now we have 3 countries in Central America, which is Guatemala, Honduras, and Salvador, and the community will work across those countries. Now, the idea is to have this joint association. La Conga and SWGO provide the expertise, the learning and training and sharing knowledge platform, remote labs, and academic links. And from LAGO, we have a continental observatory, we have the capillarity that reach a lot of institutions, because we are aiming to have a very middle or low cost instrumentation that can be funded by the institution itself or the local agency for science. We have developed a simulation framework, and we also have a working instrumentation. And that's all. Thanks a lot.
Further questions?
Mauro.
You can go ahead.
Yes, can you hear me?
Yes.
Okay, thank you very much, Luis, for your talk. I have a question regarding issues not related to physics directly, or at least astroparticle physics, for like studying and doing fundamental science. You mentioned myography, and also in your last slides, you put as an issue there seismology. Have you entertained the idea of using these myography techniques to find, for example, or to look for how do you call it? These reservoirs of water, or say reservoirs of natural gas under the seabed, or in other like scenarios, for example, also doing myography for mining.
Okay. In our case, we are using myography for volcanoes, because Central America and the northern part, and in fact, all the Andes has a lot of volcanoes. And then we think that using these skills that we learn from the astroparticle physics in this field, we'll get some better project funding and relation. But we are also very preliminary advances in very tiny detectors for muon to be used in mining. And then we can share some of the things. We start from a very tiny muon detector, which is called Cosmic Watch, from the MIT and the MIT group. Then right now we are modifying this design, trying to put in a tube and put in the well to see mining sources. Also, colleagues from LAGO that are working in Argentina are using myography to study civil structure like dam, and to see if you have some hold or cave beneath the cave structure, the dam structure. Then
because you can measure density gradients.
Yes,
right.
the myography is density gradient.
Basically,
You
yes.
use it in different scenarios.
Okay, so it's nice to know that. So you're thinking like to do service with this in other fields.
Absolutely,
okay.
Absolutely, and we acknowledge that we learn all these techniques from the astroparticle community, and then we have to have the pipeline from basic research in astroparticle through the applied research in geophysics or civil engineering and whatever. But the pipeline, the relation from the active relation from basic science to applied science is what we're building
yeah.
within the collaboration.
Okay, that's very nice. Certainly, it's very useful. I recently went to a talk from a person in the US. He was a former experimental physicist in astroparticles, and now he's working as a consultant for a mining exploring company. So they do boreholes, they put these muon detectors down, and they can see whether you can have like huge area with eventual interesting minerals and so on. And you can do this for looking for water reservoirs also, which is very important in Latin America. The access to free water, to sweet water is
from water reservoirs, and also because the Andes has very high mountains, and in these very high mountains you have the paramo places, and those places provide the water to most of the Andean cities. Then we move through the study of moisture through thermal neutron. That is why this is the motivation. And the other thing that we have a design of one of these myographers to be used in the petrochemical industry, because you are using the muons as a source. A source that is plenty in every place and is free, and then you can use to study how the distillation towers in petrochemical industry are operate, and how they are aging and have a very difficulty in provide the fluid through this very big structure. This is another application that we have been thinking and have been simulating.
Okay, interesting. Thank you very much.
Thank you very much for your question, Mauro.
What's another question there? Yes.
What type of scintillators are you using for the neutrons?
Plastic scintillator doped with phosphorus or whatever. The standard scintillation used in the OIE, because we are very small group and we cannot buy this type of scintillator. Then we use the muscle of OIE, and when all the Amiga detectors were built in OIE, we use this opportunity to buy a plastic scintillator exactly the same they're using in Amiga and in OIE.
No.
He answered my question.
Okay, perfect. Yep.
So Luis, a quick question. What is the level of funding from CTAD that you got?
Excuse me?
What is the funding from CTAD? What is the level of funding? You mentioned that you got some.
Very, very few. This is something like $12,000 a year for 4-year project. We are starting, and this is only for mobility. And then the business plan I mentioned is to have funding for different activity from different sources. That give you a headache, the managing and writing project, because it's very easy when you have a bunch of funding from one source and then you can manage all these things. But in our case, we select. We were born and we are living from getting funding from different sources. And getting funding from different sources means that you have to focus. In the particular, the CTEC is for mobility, exchange of professor, exchange of students. That's it.
That's great. It's not little. It's very, very important. $12,000 a year is good.
Well, we are 83 people.
Thank you.
Thank you. Let's thank again.
Okay, thanks a lot for the opportunity.
Now we have the break for the coffee break. We'll combine at 11.